Hello everyone, and welcome to Module 9 of INST728E, where we'll be talking about topic modeling in social media during disasters. So first off, an overview of what topic modeling is. The idea is to take a collection of social media posts and break them down into groups that are all topically or thematically connected. So here we have an example of about 10 different topics from the Brussels airport bombing, and these topics provide us insight into words that frequently co-occur together or different themes that people are discussing about this particular event. So the first question you may ask is, what exactly is a topic when we talk about topic modeling? Well, topics can be defined in multiple ways. We'll try and define them here by analogy. So you could think of a topic as a category or section in a newspaper or on Netflix. So a category in the news might be sports or metro or art or leisure, whereas a category in Netflix might be movies with a strong female lead, science fiction, irreverent comedies, these kinds of things. These are all ways of grouping together content in some cluster that makes thematic or topical sense, where all of these items are similar in some way. Another form of a topic is a hashtag on social media. So presumably when people are using a hashtag, they're using it in a similar way. So if you're thinking about my life in movies or hashtag Throwback Thursday or something like that, people who are using that hashtag are all discussing a similar topic or a similar kind of event or having a similar discussion. It could also be a collection of related words much more loosely. So the phrase Star Wars or Barack Obama or Donald Trump, these could define topics about movies or about science fiction or about politics or the 44th president or the 45th president, and you can build other words or identify documents that use these phrases of words and say these are somehow topically linked, and then those would be your topics. So how do we find these topics? Now we'll say this idea of a topic is presented relatively loosely, but that's fine. The way topics are constructed and how you interpret them changes based on the context, so there isn't a specific definition to use. For finding topics, though, there are a couple ways to do this. One is with human selection. So basically, you have a bunch of documents, and humans try and group them into a set of themes or categories or topics. Now, one way that you may have seen this is with thematic analysis. So say you have a bunch of documents or a bunch of tweets or a bunch of movies, and you view them all, and then you try and group them in ways that make sense. So for books, you may have the science fiction books over here and the fantasy books over here. Same thing with movies. You could do the same thing with tweets. Here are tweets about politics, here are tweets about sports, here are tweets about celebrities. And you have some humans sit there and try and make these categories or do this category assignment. There are also automated ways for this. Two popular ones are called latent Dirichlet allocation, or LDA, and author topic models in ATM. So we'll use both of those here in this module. Human-based topic modeling in general can be better, but as is always the case when you're involving people, is generally slower and more expensive. And LDA has been around and is generally a standard approach for topic modeling. So I'll give you a little overview of LDA before we move on. So first off, topics, whatever this nebulous idea of topics or groups may be, are hidden. They're not actually given to us within the content, so we don't have a way of directly identifying the topic that a particular message is associated with. Now, you may say in Twitter this isn't technically true since we have hashtags and we can say that a hashtag is a topic, but we'll assume that a hashtag is some underlying expression of a topic. So then we have a topic is defined for LDA as a weighted collection of words or a mixture of words. So this means that if you have all the words in the English language, a particular topic about Star Wars may have weights for things like Star and Wars and Luke or Jedi or Force or something that are much higher than weights for Mary or fantasy or sports or soccer or something like that. You'd have other topics that would have similarly different weighting schemes for all the words in the English language, where words that are most closely associated with a particular topic get the highest weight, and words that are not associated with that topic get the lowest weight. So that's a topic. The next part of LDA is a message or a document, or in our case, a tweet. And this tweet is considered a weighted collection or a mixture of topics. What this means is a particular document or a particular tweet may express or be related to multiple topics, and this is fine. So if we have a set of 20 topics and one of them is about immigration and the other one is about the 45th president, Donald Trump, then you could say, well, a tweet that mentions Donald Trump and his actions with DACA or Dreamers could be about both the topic of immigration and the topic of Donald Trump. Whereas the other 20 topics we have, or the other 18 topics we may have, may be about Star Wars or astronomy or whatever. So when you look at this message, you would say the topic about immigration has a high weight and the topic about Donald Trump has a high weight, but the other topics that we have a low weight. So this is the construct that we have, where topics are weighted collections of words and messages are weighted collections of topics. And we use the words in the message to figure out what those topics are. So for LDA, we have three main parameters to look at. The first is K, or the number of topics. Most of the topic modeling techniques we use, or clustering techniques that you may have seen before, have some parameter K that tells you how many topics you want to find. And this is going to be input into the system, so we have to choose this number K beforehand. Then we have another parameter called alpha. This gives us information about, it's called document concentration. So alpha tells us how many topics should appear in a given document. Now, what does this mean? So if you think about a tweet, where a tweet only has, well, it used to be 140 characters, now it's, I think, double that. You can only fit so many different topics in one of these relatively short messages. So you would expect the alpha value for Twitter to be low, whereas if you were talking about a book, so maybe you had a short novel, it would have many more topics in it, or it would have room for a lot more topics in it. Or if you were thinking about or talking about a long-form news article about immigration or public policy, you have much more room for different topics or for more topics to be present. So if you were doing topic modeling on news articles, you would have potentially a higher alpha value that would say we can have more topics in a given document. And the final parameter we have is called beta. This is the topic word concentration. So where alpha talks about how many topics can appear in a given document, beta tells us how many words appear in a given topic. So how sparse are our topics in terms of words? Do we expect a particular word to show up in just one topic, or do we expect a particular word to show up in many topics? So like alpha, where we have lower values mean fewer topics, lower betas mean more sparse topics. So words appear in fewer topics. Now, we contrast this with author topic models. Author topic models are very similar to LDA. The only difference is they include some additional information. LDA talks about topics are mixtures of words and documents are mixtures of topics. Author topic models integrates all of that with the idea of an author. So we can look at Twitter. We know who is tweeting a particular tweet because we can extract the author from the JSON of that tweet. And we can say, well, authors also have a mixture of topics. A particular author is unlikely to tweet about all possible topics. Instead, we have a weighted combination or a weighted set of topics for that particular author. So we can use this information to get more inference into building our topics. All right, so in this module, I'll show you how to do some topic modeling using both LDA and ATM. And what I want you to do for the homework here is, as before, fill out the Module 9 notebook with your content for your disaster or your event, and then run LDA and ATM on your tweets. And I want you to do it for 3 different values of K, so I'm not going to go into how you choose K. There's not an extremely good way to do this in an automated fashion. Essentially, you need some domain knowledge or some understanding about the event to choose a good K, or play around with values of K. And what I want you to do is, for each of these values of K, compare the topics that are returned by LDA and ATM, and then figure out which K you think is the best K for your data, and then tell us some justification about why you thought that. Okay, so now we'll move over to the notebook. So as I mentioned, we'll be using both LDA and ATM to do our topic modeling. The package that will provide this is called the GenSim package here, and we'll see when we import that in a few minutes. But now everything right here, these packages we've all seen before, so stopwords, tweet tokenizer, NumPy, all that. So we'll go ahead and import all these packages. The event description we've also seen, so be sure to update that with your event. Now we'll read in the relevant tweets that we've done for the past few modules. We'll print out their temporal ordering that we've seen several times. Now we'll do this because later on what we want to do is print out the per topic frequencies over time as well. So that'll give us some insight into which topics are being discussed when. We've talked about LDA and ATM as topic modeling algorithms, but we also mentioned that hashtags can be considered a topic in and of themselves. So this is true, right, because it gives us some insight about people who are using the same hashtag are likely discussing the same topic. So hashtag pray for Brussels, or hashtag prayer for Brussels, or hashtag thoughts for Brussels, these kinds of things. You can say these are all hashtags that represent the same kind of topic. So we can use this to get some insight into the data without really running any sort of algorithmic analysis. And what we see, frequent hashtags include hashtag Brussels, Brussels attack, Brussels airport, pray for Brussels. Now, this gives us some insight where the hashtag Brussels airport may be conversation about Zaventem, whereas hashtag pray for Brussels is likely to be content about thoughts and prayers. Now, are these two the same, or are they subtopics in the same topic, the attack for Brussels? That's sort of up to you as the analyst to decide. But you could make the claim that hashtag Zaventem or hashtag Brussels is a separate topic than hashtag Malbeek. So this is the transit station, the metro station in Belgium that was attacked. And people discussing the airport versus people discussing the transit bombing may be different discussions. One could be talking about the number of casualties at the airport. The other could be talking about the number of casualties at the metro station, or it could be conversation about both. So you might have thoughts and prayers are out with everyone, hashtag Zaventem, hashtag Brussels airport, hashtag Malbeek, these kinds of things. But it's kind of up to you as the analyst to figure out how you want to interpret this information. We'll start our topic modeling with GenSim, and to do so, we need to import a number of modules. So the main thing that we need to do, though, is a lot of pre-processing. So what this means, we've already seen tweet tokenization, but we need to go a little bit further than that. So the first thing we'll do is import all of these modules. So LDA multicore, that's the package that provides us with LDA. AT model is the package that provides us with ATM. But then we have a number of packages here that allow us to do featurization or processing of our data. So this count vectorizer, I'll tell you what that does in a minute. Dictionary will give us all the words that people are using in our relevant tweets. Phrases lets us look at pairs of words that are used in conjunction. These are called bigrams. And TF-IDF model is a method for weighting words that are very common with low weights. So if we want to do topic modeling and all of our tweets may include the word Brussels, we want to decrease the weight of that keyword. TF-IDF lets us do this. It stands for term frequency inverse document frequency. So tokens that have high frequency and occur in few documents are more important than tokens that have high frequency and occur in many documents, right? So I won't go deeply into this. This is a topic for an information retrieval course. Now you'll have some insight into what TF-IDF does. And then the first thing we'll do is remove stop words. So stop words we've seen before for English, but since we're also looking at an event that happened near France or in Belgium where people speak French or Dutch and English, and we want to include stop words in French, and we'll include stop words in Spanish as well, just in case. And then we'll add some of our own stop words here. So these are more specific to Twitter, so HTTP or HTTPS for links, RT for retweets, @ for mentions, CO, am and ampersand, ellipses, new lines. We'll go ahead and remove all of those as well. And then we have the keywords that we've been using. We'll remove those as well because all of our tweets, or the majority of our tweets, will include these keywords. And then we'll remove punctuation just to avoid any issues with that. So that will give us the first set of pre-processing. So when we tokenize our tweets, which we've seen before, we will ignore these stop words. So anything that is in this stop list, we'll ignore. Now, the next thing we want to do is convert strings of text into what's called a bag of words model. Now, what this means is rather than having a sequence of words that we see here, so my best friend lives in Brussels and my friend isn't responding, we want to tokenize that up into a set of keywords. And then instead of passing around lists of strings, we want to pass around lists of indexed numbers. So these numbers are going to be smaller in memory, so this will give us a smaller memory footprint and increase our performance. So to do this, though, we first look at all of the keywords that are present in all of our tweets. So here's an example of 3 different tweets. We would go through all of these tweets and come up with a list of all the unique words that exist in these tweets. And then we filter out our stop words that we have. And then what we want to do is replace all these tokens with indices. So then we will associate each one of these keywords with an index or an indexed number. So what this means is we'll go from this list of all the unique words in these tweets to this list of all the unique words in these tweets with an associated index value or index number that we can use to replace these words. So here we have the word friend gets the index 0, the word lives gets the index 1, the word responding gets the index 17, etc. You can think of this as kind of a map or a dictionary where if we give the key 0, then we'll return the value friend. Okay, so once we have that, then we can convert our tweets here into a real bag of words model. What this means is we'll replace each one of these words. So we'll replace the words my best friend with their indices, their numeric indices from this list here, and the frequency in which those words occur. So we'll convert this tweet, my best friend lives in Brussels and my friend isn't responding. The first token we'll look at is the token for friend. We'll see that has the index 0, so we'll show that here. And we see the word friend occurs twice. So this 0 refers to the word friend, and this 2 says the word friend occurs twice. Likewise, we have the word 3, or the token, the index 3, which refers to the word my, also occurs twice. So my best friend lives in Brussels and my friend isn't responding. And then all the rest of these pairs of numbers, so 1 and 1, 9 and 1, they tell us other words that occur in this tweet. So 1 and 1 lives occurs 1 time, 8 and 1 best occurs 1 time, 14 and 1 the word in occurs 1 time, etc. Now you can look at this other example here, wish all but the best out to Brussels this morning, as another example. So the main reason we do this is for performance reasons. So this set of text, or this set of code right here, will convert these tweets into these bag of words models, and we can print out an example. The analyzer that we get out of it will tokenize up our tweets and remove any stock words from our list of tokens. This line right here will apply this analyzer function to every tweet in our list of relevant tweets, and then we can print out what the results are. So here we print out the first tweet in our list of relevant tweets. So we get smoke of Brussels airport terminal after what sounds like 2 explosions. And then here we can print out the tokenized form of it after removing stop words. And we see this retweet token is gone. We start with the D. Schwarzer mention, smoke Brussels. We removed the of word because that's a very common word. We see airport terminal sounded, so we removed after and what. Like 2 explosions just before, so both the words just and before got removed, the word AM got removed. So this is our filtered tokenized tweet. Now the next thing we do is look for common bigrams or common 2-word phrases, and this allows us to recover some of the sequential information that's included in these tweets that we may miss if we were just using bag of words directly. So in order to do this, we'll look for pairs of words that occur at least 5 times in our text, and then we will create this phrases dictionary using all of our analyzed tweets. Bigram analyzed text will replace all of our tokens with their bigrams if they exist, and we can print out what the results are here. So this was the original tweet that we saw, this was the tokenized form of the tweet that we just saw, and here is the tokenized form with bigrams, and we see 2 explosions got merged into 1 word. And this makes sense because 2 explosions is used often in describing that there were 2 explosions at the airport. Okay, so the next thing we do is build a dictionary. So we take all of our analyzed tweets and create a dictionary from them. So this dictionary says, here are all of the words used in our entire set of tweets. And what we want to do now is filter out words that occur very frequently. So this dictionary.filterExtremes lets us drop very rare words. So this min count says we're going to drop words that occur less than 5 times. And this max frequency count says we're going to drop words that occur very often as well. So words that occur in 75% of our documents, we will drop those as well. So this will go through and just initialize our information for us. So this is boilerplate. And then here we'll create a couple of maps that will map our indices to actual words, and then reverse this and go from words to actual indices. So this will be useful when we try and print out what topics actually look like. All right. The next thing we do is we convert all of our tweets. So for all the text in our analyzed text, we'll convert them to the actual bag of words model here. So this is what this doc2bow function does. And then we'll train a TF-IDF model. So as I said, TF-IDF will downweight words that occur frequently in all of our documents. So those matter less to us. So we'll build this model from the bag of words corpus that we just created, and then we'll convert this corpus from the corpus that we had to this TF-IDF corpus. So at the end of this, we'll run this. I'll show you what one of these corpora look like. So we can see TF-IDF corpus 0. So this first tweet that we saw here includes 1, 2, 3, 4, 5, 6, 7, 8 different words, and then these are the weights for these different words. Okay, so now that we have this featurized filtered data set, we can apply LDA to it finally. Now we use this TF-IDF corpus, we set the ID to word dictionary here so then we can show the topics, and then we set the number of topics here. We'll start off with k equals 20, and as just a default value. You can change this up to any value that you want. In fact, you'll need to do that for the homework. And then once we run this and train this model, then we can take out the 20 topics and look at 10 words of the 10 top words from each one of these topics. And then we'll print out the resulting words. So this will take a second to run as it goes through and tries to figure out what the topics are. And then after that, we will print out the results. So we see topic 0 is about prayers. So we see pray for Belgium. Topic 3 is also about prayers. So pray for Brussels. We have the prayer emoji. Conversations about airport explosions in Zaventem. Conversations about airport and metro explosions in Brussels. This is probably in a different language. Tweets that probably are retweets from BBC Breaking News about a Brussels attack with explosions, and several other topics here. Now we see a lot of these topics seem to overlap, so maybe 20 is not a good number. So if we drop this down to 10, and we see airport and metro explosions, so this topic is about tweets that mention both the airport and the metro attacks. Explosions airporto, this is probably tweets in French. Here are tweets about breaking news. Here are tweets about flights at the airport. Now, as I said, you may want to play around with your K value, so you may want to start with 10 or 20, and you may even want to play around with the min and max frequency count here, or the bigram minimization count there. So we could drop this down to 0.5 and boost this up to 10 and rerun our analysis. And we see this tweet, or this topic, is probably about people who were retweeting the video of people running from Arnhem. We have a topic about thoughts and prayers regarding explosions. We have explosions in different languages, references to the airport in French, etc. So one of the interesting things that you see is topics that break down at the category level and at the linguistic level. And this makes sense, right? That words will co-occur with words in the same language more than they'll co-occur with words in other languages. So you'll see linguistically consistent topics. All right, now there's also a package called PyLDA-Viz that we can use to visualize these topics. And this gives us some insight into salient terms. So we see pray for Brussels, pray for Belgium. These are the most salient terms. Brussels and Brussels attacks, bomb, pray, explosions, the prayer emoji. So things that you might expect. There's also references to Trump here. So references to Trump were in topic 11. We can click topic 11 and see what topic 11 was. So we see Brussels airport, Zaventem, Brussels attack, news, explosions, references to police reports, and terror. See, we can click around with the other topics as well. So this one mentions suicide bombings. This one you can tell is in a different language, or mostly a different language. This one seems to be people who are mentioning Donald Trump and conflicts and BBC Breaking News and the Arnhem video. This intertopic distance map here gives us some insight into how similar topics are. So topic 4 is pretty similar to topic 20. And we see this with the words that are used. Topic 3 is pretty dissimilar. Topic 17 is pretty dissimilar. Topic 15 is pretty dissimilar. So you can explore some of the topics here using the PyLDA-Viz. All right, so the next thing we'll look at is the author topic models. So we've already done all the pre-processing that we need. So this analysis pipeline will go through and perform all the analysis that So this analysis pipeline will perform all the pre-processing that we've already configured above. And the main reason we want to do this is because we want to pull out the mapping of documents to authors, so who is writing these tweets as well. So what this line does is go through all of the tweets in our relevant tweets, and then pull out the analyzed version of the tweet, and then the user ID for that tweet as well, so who was the actual author for that tweet. And then we want to filter them out so we can drop any user ID that had an empty tweet as a result. So a tweet that may have nothing but very common keywords may get removed from our analysis, and we want to make sure that our user IDs only include users who actually have a tweet in our list. Otherwise, you get weird errors with Python that make it a little bit difficult to diagnose. Okay, so now we have ATM docs. These are all of the documents in our tweet list that have an entry or have at least one token after our pre-processing. And this doc to author is a dictionary that maps all of our user IDs to these documents. So once we run this, we'll have these two maps for us that we can then pass to the author topic model. So we have the corpus. These are all of our pre-processed tweets. We have the same ID to word dictionary that we had before, but now we also have a new dictionary for doc to author. So this maps the documents to the author IDs, and then we have the number of topics K. And then the rest of this follows what we've seen before, where we'll print out the top 20 topics and the top 10 words per topic. After a few minutes of letting that run, then here we see some example topics, and now we see the linguistic consistency is even stronger. So Malbeek, explosions, Metro Airport, these are all probably retweets from Le Monde. Here are retweets from iTelly, mentions of Brussels and Aeroporto. These are going to be tweets from BFM TV. And again, you can play around with K, try 5. And we see breakdowns across languages for solidarité, morts, muertos right there. Topic 3 is probably a whole topic just about of people discussing the video, of people running away from Zaventem, the airport. Can rerun with 10. And we see tweets from a topic for Le Monde, a topic for iTelly, references to deadly explosions, a topic from BFM TV. So you can see these topics are slightly different than the LDA ones, and they seem to be more focused around particular users, which makes sense because this is a topic model based on the idea that particular users tweet about relatively few things. Okay, so this gives us some insight into different kinds of topics or different ways we can extract topics. Now what we want to do is look at how these topics evolve over time. So what we want to do is plot the number of tweets per topic per minute. So here we want to go ahead and create a little counter that will count up the number of tweets that occur per given topic. So we go for every topic in our list of topics, or our topic count. We'll create a map of 0 counts for however many minutes are in our frequency map. So each one of these topic indices will return an array whose length is the number of minutes in our frequency map, and we start off with having all 0. So now what we'll do is go through every minute and set of tweets in our frequency map. We'll pull out the tweets for that minute, and then for each tweet we'll use the LDA model to get the topic distribution for that tweet. So we'll analyze that tweet using our analysis pipeline, get the topic distribution here, and then we'll pull out the indices for the top topic. We'll go to our topic counter map for that particular topic for this particular minute. So this I is the index into our frequency map keys, and increase that count by 1. Note I made a change here. For instead of enumerating through the keys, we'll enumerate the sorted times because we want to make sure that the times are sorted. So we'll go ahead and run this. And then here, once we have this, we can go through and create a plot for different tweet frequencies. The ticks we've seen before, the X data is the number of minutes we have, and then for each one of our topics, we'll plot the number of topic counts per minute there. And we see this relatively ugly graph with a few topics down here. So this pink topic, topic 16, gets some traction here at the bottom. This red topic, topic 3, gets some traction here early on. And then some of these topics spike up, and then other topics drop down. We see most of the topics here. But 20 topics is a little bit difficult to visualize here. So let's go up and reduce the number of topics in our LDA model. So here it is. Maybe we'll look at 5 topics again. So go ahead and run this. All right, so we have people talking about safe after the explosions. We have references to suicide bombings. We have references to Zaventem. This is probably about the video. More references to explosions at the metro and the airport. And then we have thoughts and prayers for people affected by the event. So now we have these 5 different topics. So 5 topics will probably be a little bit easier to visualize. So we go ahead and reset our topic counter, count up the number of tweets per topic per minute, and then we can graph them. So we see topic 3 is a spike here. Topic 3, let's review what topic 3 was. Topic 3 was references to explosions at the airport. So we see this big spike here, and then topic 4, we see a big spike here. So our topic 4 about thoughts and prayers spiked towards the end of the event, or after a couple hours after the event, whereas references to news spiked here, and topic 0 about explosions at the airport and at the metro station and people being safe spiked here and here. So we get some insight into how these topics evolved over time. Now, if you increase the width of these bins, so we looked at number of tweets per minute. You might look at number of tweets per 10 minutes or per hour. You'd probably see a different sort of effect where references to the event and the explosions will spike early, and then references to thoughts and prayers will spike after that. Okay? So what I want you to do is go through for Module 9's homework, go through, update this notebook with your content. So remember to update the event description and point it at your relevant tweets, and then run this, playing with the number for K, so the number of different topics that you have, and playing with the time frames to get a nice graph of topics over time. All right? At the end, post your modified notebook and some discussion describing what you found interesting or compelling about your analysis here. And that'll be it for Module 9. As always, if you have any questions, feel free to reach out on Slack.